Hi, I'm David Bonsack, Product Manager for Rheology at TA Instruments. I'd like to welcome you and thank you for joining us for today's webinar. During the webinar, you can customize your viewing interface by arranging the windows to your liking. You can resize video and slide windows independently from one another by clicking and dragging at the bottom right-hand corner of each window. If you get disconnected at any time, please use the instructions you've received to log back in. You can access several different content windows by clicking the widgets at the bottom of the screen. These include speaker bios, additional file downloads, and social media interactions. If you need help, click the question mark widget. Please ask any questions you may have at any time during the presentation by submitting them through the Q&A window. We will answer as many as possible of these at the end of the webinar. Our guest speaker today is Dr. Alina Latshaw of TA Instruments. Dr. Latshaw is an applications engineer with TA, where she supports customers in the areas of rheology and dynamic mechanical analysis. Prior to joining TA, she completed her master's and PhD under the supervision of Professor Saad Khan at North Carolina State University, where she developed novel methods to improve throughput in electrospinning processes and used rheology to characterize the curing processes of several different chemistries. It is truly a pleasure to have Dr. Latshaw with us today. The title of her talk is Tribo-rheometry, Quantifying Friction Between Surfaces Using Rotational Rheometers. Alina?
Thanks, Dave. Hi, I'm Alina Latshaw, and today we'll be talking about tribo-rheometry in a way to quantify friction between the surfaces of your rotational rheometer. In this presentation, we'll be discussing the theory behind tribology, introducing the Tribo-rheometry Accessory for the rotational rheometer, and then going through a few case studies that we've performed in-house and discussing some of the data that we can get from these types of tests. Now, the word tribology can be derived from two words. The first word being tribos, which is Greek, meaning rubbing or to rub, and then the suffix ology, which is literally the meaning the study of. So when we put these words together, tribology literally means the study of rubbing or the study of things that rub. So this can include properties such as adhesion, friction, lubrication, and wear. Another way to think about it is tribology is the study of friction, wear, and lubrication between two interacting surfaces while they're in relative motion with one another. Now, we experience this phenomenon every day, whether it's between the gears in your car engine, the brake pads on your car when you're braking on your way to work, or even applying cosmetic and personal care products onto your skin to moisturize your skin. Whether we're chewing food or drinking drinks and the mouthfeel in our mouths, or even in artificial joints for prosthetics, which are designed to mimic the feel and the movement of natural joints. Some of the aspects of tribology will then include studies such as friction, or the forces between these moving materials and these moving surfaces, things such as abrasion, whether these surfaces will undergo any type of surface damage while they're moving past one another. These tests can also be done in either dry or lubricated conditions, so solid or liquid lubrication, also lubricating between oils versus greases and different kinds of formulations. Another aspect of it is going through and studying the influence of surface modifications and coatings and how that affects the coefficient of friction between two types of materials. Now, taking all of these aspects, tribology will then be related to a product performance, its reliability, its wear, so how quickly do we need to maybe replace these oils and greases, how quickly do we need to replace gears, for instance, or these two surfaces. And then also in some newer areas in the food and drinks industry, things such as mouthfeel, how a consumer perceives a product when they're consuming it, or even tactility, so how these personal care products or things feel to us on our skins. The way that we measure coefficient of friction, or the way that we quantify it, is coefficient of friction, which is mu. And the way that we do this is we take two surfaces and we put them in contact with one another and push these surfaces together through a load force, so the force that's moving perpendicular to the motion. And then we're going to move one of these plates and we're going to kind of slide them past one another. So now one of the surfaces will have a direction of motion. They're going to be pushed together in contact with one another through the load force, and then some frictional force is going to oppose the motion that one of our surfaces is going through. So again, in between these two surfaces, as you can see in the diagram. So the coefficient of friction is just simply the frictional force divided by the load force, or you could think of it also as the ratio between shear stress and normal stress. Now, if we zoom in on all of these surfaces, right, so on a macroscopic scale, things such as stainless steel or polymer bars, they look really smooth on the macroscopic scale. But what we're studying with tribology is the interactions on this microscopic scale. So if we zoom in between these surfaces when they're in contact with one another, you'll see all of these surfaces are somewhat rough on a small length scale, so maybe microns, nanometers even. And all these roughnesses in the surfaces are known as surface asperities. Every material will have its own unique characteristic of the surface asperities, and it will depend on things such as the composition of the material, also the way that these materials were processed, for instance, things like that. So when we push these materials together, we're looking at the interaction between these surface asperities. When we have a small load force, for instance, these surface asperities may not be interacting with one another too much, but it's still something to consider. So you can see in the larger diagram, those surface roughnesses they're interacting, but maybe not all of them are participating in the interaction. However, if we increase that load force and now we push these materials together even further, now you could see in the large load force diagram, all of these surface asperities are starting to be in contact with one another. Another way to think about it is if you have in your room, say you have a small mouse and then you have a really large elephant on your carpet. So you could think of the carpet fibers as a surface asperity, right? So there's a little bit of roughness on them. Now when we have the small mouse on the carpet, it barely touches it. You don't really see the carpet fibers move or flex at all because they're not really being interacted with one another or with the surface of the mouse. However, if you have an elephant, which would represent the large load force, you can always see those carpet fibers are going to kind of compress with one another. Now, surface asperities may not compress, but they're still interacting with the other surface. So how do we put this onto a rheometer, right? So we have these surfaces. Again, these plates come into contact with one another, so we need to control the force between them, and then we're going to also apply movement to one of the surfaces. So an accurate tribology measurement will require that we have direct contact between these two interacting surfaces. So we need to have a way to control and apply the load force. In the rotational rheometer case, what we're doing is we actually have the load force acting in the axial direction, and then when we're moving one of the surfaces, a rotational rheometer will have the movement be in the rotational direction. So again, as you could see in the diagram, we have the load force in the axial direction, and then the movement's going to be in the rotational direction. Now, the other aspect of an accurate tribological measurement is going to be relative motion between the two surfaces. So again, in a rotational rheometer, this would mean we need to have excellent angular velocity control, or the movement in the rotational direction. So again, all of these things, whether it's axial force or angular velocity control, we already control and apply these on our rotational rheometers very well, just for our simple everyday rheological measurements. And so it just made sense to bring this tribology accessory into our rotational rheometers. The thing we need to consider is now we need a way to provide good alignment between these two surfaces, because as I mentioned, we have these surface asperities which are not uniform throughout all of the surface, but we want to make sure that we uniformly distribute that load force between all the surfaces in contact, not only when it's standing still, but also when we're rotating or when they're moving past one another. And as these surface asperities move past one another, we're going to have different length scales, if you will. So we need to provide a way to make that axial force uniformly distributed. The way that we do that in our tribo-reometry accessory is by adding what we call the beam coupling. Now you could see in the picture, for instance, it's exaggerated, for instance, but you have your bottom surface, which may have a little bit of surface asperities, and then you have your top surface. In this case, it's depicted as a ring, but you could see that the spring or our beam coupling allows these two surfaces to stay in contact with one another, uniformly distributes all of that axial force between all of the modes of contact, while also providing that while we rotate. So what this beam coupling does is, you can see we offer a stainless steel coupling and an aluminum coupling, but what it does is it introduces axial compliance, so compliance in the axial direction, without compromising anything in the angular stiffness. So we want to make sure we have excellent control and excellent stiffness in that rotational direction so we can make that torque measurement and hence the frictional measurement. But we also want to make sure that there's a little bit of compliance to make sure that our surfaces stay in contact and don't lose contact with one another and then move up and down like this. We want to make sure that everything's always in contact with each other. So the helical spring that we use in our beam coupling ensures this good alignment between the two surfaces. And then it's also a self-aligning coupling. So as we're rotating and as things are changing a little bit throughout our experiment, the coupling will self-align and it will provide that smooth axial force control while maintaining the angular stiffness. Some things to know, as I mentioned, we do offer two. It comes in the kit. We have the stainless steel coupling and the aluminum coupling. The stainless steel coupling, since it is stiffer, we do recommend using it for axial or for load forces greater than 6 newtons. But since the aluminum coupling is a little bit softer, we recommend nothing greater than 20 newtons. Now, all of this accessory is compatible with all of our DHR rheometers and our Aries G2 rheometers. We can have temperature systems and temperature control with either the Peltier plate or advanced Peltier system, and the ETC oven or the FCO oven. The temperature ranges can go from -150 all the way up to 350, so if you're doing such studies such as mouthfeel or body temperature, we have control up to that temperature, or if we're doing studies at elevated temperatures, we have the ability to do that as well. The maximum axial forces, as you can see, will vary based on the instrument, but the maximum torque that you can apply is still 200 millinewton meters in torque. All of these variables, so all of the tribology related variables are going to be directly incorporated into the Trio software. Clearly for you, things such as sliding speed, the sliding distance, the load force, the friction force, coefficient of friction, and the Gumbel number if some of the information is applied. But all of those will be supplied within Trios and calculated directly for you. Now, our accessories come in 4 flavors, if you will. We have the 4 different geometries. We have the ring-on-plate geometry. As you can see, we have a ring, and then it's in contact with a bottom plate or a bottom surface. Also, the 3 balls-on plate, which on the top, instead of a ring now, we have 3 hemispherical spheres and the plate on the bottom. And then on the other one, you also have a ball on 3 plates. So you can have a ball, and then the 3 plates are at an angle with the sphere. And then you can also have the 4 balls, which has 1 sphere on the top and then 3 spheres on the bottom. Now, if you notice, all of these have a modular design. So what that means is that it's easy to switch back and forth between the different geometries depending on what types of materials you're studying. It's an easy method to interchange them. All of these tests can also be performed in dry or lubricated conditions depending on what's of interest and what the application is. And then the last thing is that the geometry surfaces can be easily customized. So all of these are standard stainless steel, but if you have things such as skin mimic or papillae, like on the tongue, for instance, if you want to do mouthfeel, or if you're studying prosthetics, then maybe you're looking at some coatings, coated materials, or even polymers. You can customize the geometries as you see fit. So what we're going to do now is we're going to go through each individual geometry, kind of give you a little bit more specifications and some more information about them. So first up is the ring-on-plate geometry. As you can see, we have these. You can have a full ring. If you flip it upside down, you can even have a notched ring, or what we call the half ring. So what this half ring allows is the notches allow for some low viscosity lubricant to continually flow and coat the substrates during the test. So if you're studying anything with lubricants, notched ring's really the way to go. Because we have a defined geometry or defined dimensions of this ring, we can actually calculate out the stress, the frictional stress. So again, there's the defined contact surface area, so you can calculate friction and normal stresses. And this geometry is really best suited for softer substrates because of this large contact area and the wide diameter. It's just a little bit easier to control. The way that you would customize this geometry is simply to adhere or attach, maybe using double-sided tape. You can attach anything to the bottom plate or cup, whether you have lubricant, then you have a cup so the lubricant doesn't fly off everywhere. Or you can adhere it even to the surface of the ring and put those materials in contact with one another. Okay, but the thing to keep in mind is that in this case, because our surfaces are perpendicular to one another, the load force is going to be equal to the axial force that we're calculating. On the 3 balls in plate geometry, now again, we have 3 hemispherical balls on the top, and then it's going to be in contact with a plate at the bottom. So these upper spheres provide point contacts with the bottom substrates. Because it's a point contact and we don't know the actual full contact area, we don't automatically calculate stress, although if you wanted to and you wanted to go through and figure out what the contact area is, you're more than welcome to calculate out the stress yourself. But this material, or this geometry, is better suited for hard and stiff substrates because of that point contact. It's easier to not max out all that axial force. The way that you would customize this geometry is simply by attaching any type of substrate to using double-sided tape to that bottom plate or that cup again. If you can find some threaded hemispherical spheres, you're more than welcome to attach those to the upper plate as well. For the ball on 3 plates geometry, it's a little bit different. You can see here we have a cup where the 3 plates are actually situated in at an angle. And then the upper geometry has a chuck where we can place a 1/2 inch diameter sphere. Now, this upper sphere, again, will provide point contact between the 3 different plates. So again, it's a point contact, meaning we don't automatically calculate out stress. But because of that point contact, this is really great for hard and stiff substrates. This geometry is also very good if you have lubricants that will flow under gravity, because since it is at an angle, the lubricant will always flow back in to, again, fill in that point contact, ensuring that there's lubricant throughout the entire test. The way that you would customize this one is if you have a stiff substrate, you can choose 2 different ways. If you have a stiff substrate in rectangular plates, you can actually machine them to fit instead of the stainless steel plates that come standard with this kit. You can place them in and replace those plates with types of polymers if you want. Or if you want, you can also order 1/2 inch diameter spheres and simply replace the stainless steel sphere in the upper geometry. So this is a really great way to customize the geometry setup if you have multiple types of materials, such as like a titanium sphere, for instance, onto maybe a coated polymer plate for any type of prosthetic testing. And lastly, we have the 4 balls geometry. So again, it uses the same upper chuck. It uses a chuck to hold the upper sphere, and then the bottom will have 3 spheres, in a container. So they're all arranged in triangle pattern with one another. Again, this upper sphere will provide that point contact with the bottom spheres, and this setup is actually really great for lubrication testing. This has also started being used in some asphalt testing as well. So there's that. The way that you would customize this geometry is simply by replacing those 1/2 inch diameter spheres with other spheres very similar to what I just spoke about on the ball on 3 plates geometry. Again, it is important to mention when using this specific geometry, all of the spheres should be tightened so that they're held in place and don't roll. We just want these materials sliding past one another. We don't want them to be rolling necessarily as well. So when we think about the coefficient of friction, we've talked about, we have this load force, we have the sliding velocity that can affect the coefficient of friction, we have these different materials, their surface disparities, and there's a lot of different categories or different parameters that can start affecting the coefficient of friction. What I've done here is I've actually kind of categorized them into 3 different areas. So one of which would be the surfaces themselves will play a really large role in the coefficient of friction. The surfaces, you can change the materials of construction, or the modulus, which would again change the modulus of these materials. So things such as plastics versus metal versus maybe a skin substitute, they're all going to behave very differently than each other. And so the materials of construction is something to consider of what mimics your application the most. Also, the roughness of the surfaces. So what's that size scale of the asperities? Are they really small? Do you have a relatively smooth surface? Or is this a surface that's actually quite rough? Because again, that's going to start playing a role in things like abrasion and the coefficient of friction. Also, do we have a coating? Is there a coating on these surfaces? If we do, what kind of coating is it? What's the material of the coating? How thick is that coating? Things like that are going to play a role in the coefficient of friction. And then also the lubricant properties, so things such as the viscosity of that lubricant, the formulation of that lubricant, what's going to happen. Now, when we talk about the test parameters, we can define things such as the sliding speed, so how quickly are our surfaces sliding past one another, what temperature is this test being performed at, and then what's the load force, so how much force are we applying when we push these two surfaces together. And then lastly, you can also look at the geometry. So we've talked about 4 different geometries. What kind of area of contact do they have? Is it a point contact? What is the geometry of that contact? And then what's the contact stress? So all of those will play a role in the coefficient of friction. So as you can see here, specifically when we talked about the different surfaces, the coefficient of friction isn't just any type of property, it's a system property. It will depend on the geometry that you've chosen, the test parameters, and then even just what kind of surfaces that you've chosen to do this testing on. So that's definitely something to keep in mind, is that it is a system property. So when we change materials out, we would expect the coefficient of friction to change. So what are some things to consider when we're doing this coefficient of friction testing on this tribo-reometry accessory? Well, first of all, again, we've talked about the wear and the friction is going to depend on the chosen surface materials and the system that we're studying. And by system, I mean the geometry that we're studying. So we can look at the coefficient of friction as a function of the angular velocity, the sliding speed, what kind of torque are we applying. So again, angular velocity would be how fast are we rotating, which will directly relate to the sliding speed of your materials. And then the torque, how much torque is applied when we're rotating these surfaces past one another. And so when we're designing a test and we're trying to figure out what to do, these are all the things that we need to keep in mind and decide ahead of time while we're doing these tests. The coefficient of friction will also heavily depend on the load force. So sometimes like, well, what load force do I use? I'm not really sure what I'm doing. And a good approach is really to choose the load force that simulates the type of application that you're doing. So for mouthfeel applications, we typically tend towards lower load forces, so they'd be like 1 to 3 newtons. Or if it's something like greases and oils and engines, maybe we're looking at more of a heavy load because we want to see, because those gears are really going to be compressed against one another. So these are all things to keep in mind. Now, if someone's interested in studying the wear patterns on some of these softer substrates, that can be analyzed externally. So after you run your test, you could take these plate surfaces and then look at them through a microscope to see what the surfaces look like before and after the testing, to see what the wear patterns are, or how much of the surface has been worn down. And then one last thing is if we are operating at very high temperatures at these really high rotational speeds for a long period of time, then we can consider using motor cooling. And if you're not familiar with motor cooling, just check out our Trios online help. It will tell you how to set everything up. Okay, so now what we're going to do is we're going to transition into some of the case studies using the Tribo-rheometry Accessory and generate some data, so show some data that we've generated. The first case study that we're going to go into is the ring on plate, and what we did is we looked at different lotions. And so the objective of this test was really to compare the coefficient of friction of 4 commercially available lotions, and how does that pertain to how it feels when a person is applying this lotion onto their skin. The system that we chose was a Peltier plate and the ring on plate geometry. So we chose a Peltier plate because it's easy to control near body temperature. And then the surfaces, so as we've mentioned, surfaces are very important. So it's important to say what kind of surfaces we're studying. In this case, we did skin substitute on skin substitute. So then it's mimicking like a hand together or when someone's applying lotion onto their skin, rather than looking at the interaction between stainless steel and stainless steel. The samples that we used were Vaseline hand lotion, Aveeno hand lotion, an Olay Total Effects face lotion, and then the Eucerin body lotion. Again, all of these are commercially available. And then the test procedure that we did is we just did a simple flow ramp from 0.1 to 100 radians per second. So again, now our surfaces are going to start moving slowly and then again start gaining speed as they slide past one another. The load force again is 3 newtons because we want to just kind of simply mimic how much force an average user would be applying when pushing their hand to their arm or their leg. One thing to note is that this is a destructive type of test because again we're pushing these surfaces in contact with one another. So it's really good to change out the substrates for each experiment. So we would be replacing the skin substitute after each experiment. What we did find is that, so in this case we used the ring on plate, it's good to trim the sample to improve the reproducibility. Now, it's easy to load a large glob of lotion on the geometry, but all of that extra lotion around the surface, very similar to traditional rheology testing, is going to add a little bit of extra drag, which can increase your coefficient of friction. When we're looking and when we're thinking about tribology, we need to get out of this big bulk rheology type of thinking and focus more on a thin film, because that's really what we're looking at. We're looking at these macroscopic surface asperities, how they interact with one another, and then how do they interact with one another in the presence of these thin films of lotions. So what we found is that trimming these samples is actually helping the reproducibility. So all I did here is I put some lotion on the skin substitute on the bottom plate. The ring itself was applied, had some skin substitute applied to the surface, and then they were brought in contact with one another. Took a trimming tool and just kind of scraped off all of that excess lotion around the edge. You may want to go on the inside a little bit too, but again, getting rid of that excess sample helps reduce the amount of excess torque during the test. So here's just an example. It's the same exact test, same exact lotion, 2 different loadings of the same lotion, but we trimmed it. And so as you can see here, we have excellent repeatability between sample loadings when we use that trimming technique. So you can see the dark blue and the light blue circles, they overlay really well with one another throughout the entire test. So now if we look at the coefficient of friction as a function of sliding speed, so again, coefficient of friction on the y-axis, the sliding speed on the x-axis, and this is studying different types of lotions, right? So in green, we have the Eucerin body lotion. In purple, we have the Olay Total Effects face lotion. The Aveeno is in orange, and then the Vaseline is in the blue. And as you could see from the pictures themselves, you could see they're actually quite different types of lotion, so we would expect different coefficient of friction behavior. And so again, we started at a velocity of, I think, 0.1 all the way up to 100 radians per second, and you can see the shape of the curves are significantly different from one another. What we did here is we kind of pointed out the application window, or the speeds which mimic most likely what people are doing, or the speeds that people are using to apply these lotions onto their skin. And so that's ranging from about 10 to 100 millimeters per second or so. Again, it's just a guess. But you could see here, so the Eucerin body lotion shows that it has a higher coefficient of friction through that application window, whereas the Aveeno hand lotion had a lower coefficient of friction. And so it's basically a way to quantify the fact that these lotions do feel different than one another. And then we actually did perform a sensory panel in-house with these 4 lotions, and it was in fact determined that the Eucerin body lotion felt a little thicker and greasier compared to the Aveeno hand lotion or the Vaseline lotions, which some people said felt a little bit more watery. But they're different kinds of lotions, one's for body, one for hands, so depending on the area of the body, you might want different properties of your lotions. But it is a way to distinguish between these 4 different lotions, and it does relate to how people are perceiving it when they're applying it. Another experiment that we performed, another case study, is in the realm of structured lubricants. And so in this specific study, we had 2 lubricants that were submitted, and we wanted to compare the coefficient of friction of them at different sliding speeds, and also try to measure the static coefficient of friction. So the static coefficient of friction would be how much force or what's the friction that we need to overcome before it starts moving. So it's kind of similar to a yield stress of a material. In this case, we used the Peltier plate and the ETC because we did room temperature and then we did elevated temperature testing as well. And we used the 4 balls geometry because, as we mentioned, this is really great for lubrication type testing. All the surfaces were 1/2-inch steel or stainless steel spheres because this was being used in an engine type of application, so we wanted to mimic the surfaces that we were studying. The samples are lubricant A and lubricant B, and again we did the test procedures. So in one we controlled the torque, and then in another test we controlled the angular velocity. Again, different temperatures, 25 and 180 degrees C. And then in this case, we did a much higher load force to mimic the application of these greases in the engine. Again, the substrates were inspected and cleaned thoroughly for each experiment and then replaced. So in this case, we did the static coefficient testing. And so you can see we have the coefficient of friction on the left-hand side and then the sliding speed along the x-axis. And so this test specifically was a torque-controlled test, so we apply a certain amount of torque and start ramping the torque until we start seeing that the materials start moving past one another. So again, it's very akin to a yield stress type of experiment where we don't see any movement in our geometries until the yield stress is reached, or until stress higher than the yield stress is reached. Same idea, except we don't see any type of sliding speed until the static coefficient of friction is reached. So as you can see here in blue, we have lubricant A in triangles, and then in green squares, we have lubricant B. And the point at which they start sliding at 500 microns per second, so this is actually quite low speed, but you could see that that lubricant A is lower than lubricant B, or the static coefficient of friction of lubricant A is lower than static coefficient of lubricant B. So one could say that the lubricant A would be more effective at room temperature than lubricant B because it will start allowing the gears and the engine to start moving sooner. Okay, so why do we want to know about lubrication? What do we use lubrication for? Lubrication is the process or technique that you can use to reduce friction between two surfaces and when they're in relative motion to one another. So what you'd want to do is place a lubricant between those surfaces or some type of material. So this could be either solid or liquid lubricant. And it really is to reduce that friction between these two surfaces. So you can imagine how a car would operate if you didn't have any type of oil or lubricant in there. It wouldn't run very smoothly at all. So we're really happy about the study of lubrication. But the analysis of lubrication, you can look at two different things. One is the Lambda Ratio, and so this is going to be the ratio of the fluid film thickness to the composite surface roughness. So when we talk about those length scales of the surface asperities, the Lambda Ratio is the ratio of the fluid film thickness, so how thick is the film of your lubricant between those two surfaces, and how does that compare to just the natural surface roughness or the length of the surface asperities. The other thing that's very common is to look at the Strybeck curve, and so that's really a coefficient of friction as a function of sliding speed. So when we look at a Strybeck curve for a lubricated system, again, coefficient of friction on the y-axis, sliding speed on the x-axis, you'll see here that some Strybeck curves tend to look a lot like this diagram here. And you can see there's three very distinct regimes. The boundary lubrication, the mixed lubrication, and then the hydrodynamic lubrication, which we'll go into in a little bit. But the benefit of the Strybeck curve is that it really captures the coefficient of friction's dependence on load force and angular velocity. So now one of these tests you can perform just by increasing the angular velocity at a constant load force. And so you could repeat these steps, or you could repeat this test at different load forces to see how does the load force change or shift your Strybeck curve. When we talk about the boundary lubrication regime, so you notice that's at the very beginning of this Strybeck curve, we're talking about direct solid-solid contact between our surface asperities. So you can see here we blew up the picture in the bottom right. So in blue you have one of your surfaces, in orange you have another surface. Yellow is going to represent the lubricant in between those surfaces. Now those black circles are there just to kind of highlight the fact that these surface asperities are in contact with one another. And the load at which we're applying, right, so these are being compressed with a certain load force, that load force is being carried by these contact points, so the solid-to-solid interaction. You could see that the system is able to move at very low speeds in the boundary lubrication regime, and typically this lambda ratio is less than 1.2. So that really means that you have a very, very thin film layer compared to the surface asperities of your two surfaces. Now, the bulk flow properties of the lubricant will play little to no role in the wear because, again, it's just in between the surface asperities, but all that load's being carried by the contact points. And so in this specific regime, you could see we have a very high coefficient of friction, so it's a regime of very high friction and wear. Now, if we start moving to higher sliding speeds, now we can start moving into the mixed lubrication regime. So in this case, you have a little bit of contact between some of the asperities, but not all of them. So sometimes the bulk lubricant and the thin film between these surface asperities is going to be supporting most of the load. So you end up seeing a decrease in the coefficient of friction because now the surface asperities aren't scraping past one another. They actually have a lubricant in between them. So now the system's able to move at low to medium speeds, and then your lambda ratio is typically between 1.2 to 3, and then the regime is of moderate to little wear. This is typically seen by a big drop in the coefficient of friction, and then you'll see an increase in the sliding speed. So as you can see here in the graph, now if we look at those same surface asperities, now they're separated out a little bit because that lubrication, that thin film, is in between the surfaces. The last area of the Strybeck curve would be the hydrodynamic lubrication. And so now this is when we're moving at really high speeds and we have no solid-solid contact. So 100% of that load force is going to be supported by our thin fluid lubricant film. So you could see here in the picture, none of our surface asperities are touching one another. That lubricant is in between the surfaces and supporting all of that load. You could see the velocity is much faster than it was in either of the other two regimes. But we see this increase in coefficient of friction, and now you might wonder, it's kind of strange seeing that, right? Because all of our surfaces aren't in contact with one another. What's going on? Why is my coefficient of friction increasing? And it's actually because of hydrodynamic pressure. So as these surfaces are moving faster and faster past one another, now we get a little bit of turbulent flow inside of the fluid film itself. And so now that fluid's going to push those surfaces apart as it supports that load. So now we have an increase in the coefficient of friction due to the drag and those hydrodynamic forces in the lubricant. The lambda ratio in this area is greater than 3. And the system's able to move at really high speeds. But this is a regime where you see very little wear. So it's good to see, at what sliding speed does my boundary lubrication, my mixed lubrication, and my hydrodynamic lubrication areas start, because that will tell us, okay, how maybe this formulation is good for one specific application, maybe this formulation is not good for an engine, things like that. So in this specific case, if we go back to our data, now we're looking at lubricant A and lubricant B, and you could see here in our diagram we have very clear boundary lubrication regimes, very clear mixed lubrication regimes, and then you can see the coefficient of friction starting to increase when you hit that hydrodynamic lubrication regime. So you can see here, so we have lubricant A is in the light gray and lubricant B is in the dark gray. And all of this testing was done at 180 degrees C. So now this is at elevated temperatures. And what you could see is that lubricant B just has a constant lower coefficient of friction overall compared to lubricant A. And that the hydrodynamic lubrication regime is shifted out a little bit. So in this case, you could say that the lubricant B would be better used for high temperature applications. So in this case, what we're going to do now is kind of switch gears a little bit and talk about mouthfeel. So this is a relatively newer area that's coming to fruition, but as far as using tribology is concerned. But with mouthfeel, you want to look at how a product's chemical and physical interaction is within the mouth. So this is pertaining from all the way starting from the initial perception when that food or drink is first entered into the mouth, mastication as it's being chewed and moving from a large material down into smaller length scales, down to swallowing, and then even the aftertaste of what remains, so those thin films that remain in the mouth afterwards. And a lot of times this mouthfeel, not only is taste a big factor, but mouthfeel is directly related to whether a consumer will accept a new product or not. Oftentimes these are qualified using sensory panels, but the question is there a way that we can use tribology to not necessarily get rid of sensory panels, but to maybe weed out some formulations that may fail in a sensory panel? So without having to go straight to the sensory panel, can we use tribology to kind of quantify mouthfeel or at least get some idea of what's going on? So when we talk about food, right, we're looking at things going from macroscopic properties all the way down to surface properties, because you have these length scales, these hierarchies of length scales and structures inside of a food product. And as a consumer, as this food is chewed and swallowed, those length scales and those hierarchy structural scales are going to start breaking down. So when we're looking at macroscopic properties, you could think of, like, let's think about chocolate, for instance. When you have a macroscopic property, that's going to be something like a big chocolate bar, right? So maybe that's on length scales greater than 100 micron. So how is the snap of the chocolate bar? What's the modulus of it? But then when we move to bulk properties, now we're looking at less than 100 microns. So that could be more related to rheology and the interaction of the fat content and the crystals and how those interact with one another on that length scale. But then when we talk about surface properties, now we're looking at the less than a micron into the nanometer range. And so that's going to be more in the realm of tribology. And so that's really those thin films that remain in the mouth or as someone's consuming these products. So for this case, we went with chocolate because that's everybody's favorite food. And we have, in this specific case, we wanted to compare the coefficient of friction of chocolate with varying cocoa content. So in this case, we had the ball and 3 plates geometry, and we used a 1/2-inch stainless steel ball in the upper geometry and skin substitute. So we took skin substitute to cover up the 3 plates, so then it kind of mimicked more of what was going on in the mouth. We looked at white chocolate, semi-sweet, and 100% cocoa, and again, did this testing at body temperature with a load force about 3 newtons. And again, to note, substrates were replaced for each experiment. So what we did first is we wanted to do just typical rheology. So we used a cone and plate, 40 millimeters, 2-degree cone, and we did a straight viscosity curve of these melted chocolates. And you can see here, so we have white chocolate in blue, semi-sweet in red, and then 100% cocoa in the green. And you can see that all the curves look really great, but if we use the Casson model to model these different curves, you could see that the yield stresses were a little bit different, but at the infinite rate viscosity, right, which would maybe mimic more of somebody swallowing, their infinite rate viscosities were very similar, ranging from 3.1 to 3.9 Pascal seconds. And so in that case, the chocolates were not very different from one another, but everyone knows that white chocolate and 100% cocoa are going to feel a little bit different when you're chewing them and when you're those thin films. So even though we had similar viscosity profiles, despite the differences in cocoa content, can we use tribology to distinguish the behavior of the different materials? And so that's exactly what we did here. So you have the coefficient of friction in the y-axis and sliding speed on the x. And we have the white chocolate in blue, the 100% cocoa in green, and then the semi-sweet chocolate in red. And as you can see here, they have very different behaviors as far as tribology is concerned. So one could say that tribology could be used as a way to get an idea and relate this to sensory panel results and try to get an understanding of what these will feel like in a sensory panel or quantify the coefficient of friction and mouthfeel. Another experiment that we did for mouthfeel was with yogurt. So we wanted to compare the coefficient of friction of commercial yogurts that had varying substrates and fat sugar content. And so in this case, again, we used the ball and 3 plates geometry. We did two actually different types of spheres to demonstrate how changing the surfaces would change the coefficient of friction. So we have a 1/2-inch stainless steel ball on skin substitute, and then we also have a 1/2-inch Delrin, or it's a type of plastic ball, on skin substitute. The different yogurts we used were 2 versions of Yoplait and then 2 versions of Faye yogurt. And then in this case, we actually just did peak cold, so we wanted to just do one constant rotational rate and to see what the coefficient of friction was at that specific rate at a load force of about 1 Newton. So the way that these 4 yogurts differed, we wanted to make sure that we had some baselines, but the Yoplait yogurts actually have added sugar and cornstarch, which are used as modifiers, and then the Yoplait original contained gelatin. The amount of protein was differed in each one as well, and then we threw in a Faye Greek 2% yogurt to compare with the Faye non-fat yogurt to see what the effective fat content was on friction without changing any other variables. So as you can see here, we've got all of our different types of yogurts. Some included cornstarch, others didn't. They had different sugar contents, different protein contents, and different fat contents. But you could see with the Faye yogurts, the only difference between them was the percent fat. So what happened? Well, we have the coefficient of friction on the left-hand side, and then we have time on the x-axis. And first, what we have in triangles is the steel on steel. So this was a stainless steel sphere on a skin substitute of stainless steel plates. And you can see here, so in dark purple, we have the Faye Greek non-fat versus the orange, which is the Faye Greek 2%. And so that had a little bit more fat added into it. The Yoplait Greek vanilla in green, and then the Yoplait original French vanilla in blue. And you could see that the French vanilla had the lower coefficient of friction, whereas the Faye Greek non-fat had the highest. But the Yoplait Greek vanilla and the Faye Greek 2% had actually very similar coefficient of frictions throughout the entire test. Now, if we change the surfaces, because we've been harping on the fact that changing surfaces will change the coefficient of friction, if we look at the different surfaces, now we have a Delrin ball on transport tape. So again, the Delrin ball is going to be a little softer than the stainless steel sphere, but you could see here that the trend is actually quite similar. So even in this specific case, the coefficient of friction quantitative value is different. The trend between all of them is still the same in this specific case. So we had the Faye Greek non-fat had the highest coefficient of friction, original French vanilla had the lowest, while the Yoplait Greek vanilla and the Faye Greek 2% had similar coefficient of frictions in the middle. But again, you could see here that the coefficient of friction is greatly impacted by the difference of the surfaces. So in summary, the coefficient of friction is not a material property, but it is a system property. So it will depend on the 2 surfaces that we've selected, the characteristics of the surfaces themselves, what kind of lubricant, whether there is a lubricant, what type of lubricant, viscosity of the lubricant, and then what are the testing parameters that we're looking at? What are the load forces, the temperatures that we're testing? So all of those are going to affect your coefficient of friction. But what we've proven is that this Tribo-rheometry accessory is able to quantify the coefficient of friction on our rotational rheometers in very many different applications. So we looked at tactility, lubrication, and mouthfeel. The coefficient of friction as a function of sliding speed will depend heavily on the interacting surfaces in the lubricant. It will depend on the temperature, but we also saw that by using a torque ramp, you can quantify the static coefficient of friction with our materials, which is great, and that it is kind of akin to a yield stress type of test. And then lastly, if we have consistent sample volume and loading techniques, we can enhance the repeatability of these measurements. So all of that excess sample around the geometry can add those drag forces, which will give a slightly higher apparent coefficient of friction. So if you have any questions about tribology, or you want to get in touch or find out more about what TA has to offer, visit our TA Tech Tips on YouTube. We have a lot of great short videos of how to set up certain tests and introductory to certain accessories as well. If you're interested in this specific accessory, you can contact your local TA sales representative or our applications at tainstruments.com. And then if you're interested in any type of on-site training or e-training courses, make sure to check all those out on our website, www.tainstruments.com. And thank you for your time.
Thank you, Alina. A recorded version of this presentation will be archived and available through the TA Instruments website.